Hi, this is Miss Hearn. Let's get started. In this video, we're going to talk about Unit A3 in my MGF 1130 class at Broward College. The topic of this class, this lesson, is measurement. We've been talking about measurement. Last class, we talked about using rulers to measure. We looked a little bit at the Pythagorean theorem. In this class, we're going to be continuing our talk about measurement, but we are talking about measuring things indirectly. And the way that we're going to measure things indirectly is we're going to take an object that perhaps is too big for us to measure, and we're going to compare it to something that's the same shape but a smaller size. In order to have this conversation, we need to know a little bit about degrees, which is the way we measure angles. So you might have heard that in a full circle, like the one that we see here on the left, we say that we can divide the circle into 360 little pie-shaped pieces that we call 1 degree. The little circle means a degree. And there are 360 of those going around. So, for example, if we're talking about half of a circle, well, half of 360 is 180. So there are 180 little pie-shaped pieces, little pie slices in 1/2 of a circle. And if we're talking about a quarter of a circle, 1/4 of 360 little pie slices is going to be 90. So this would be 90 degrees. We talked about 90-degree angles last time when we talked about right triangles and the Pythagorean theorem. We can also break down angles even smaller. So here you see our 90 degrees we just talked about was a quarter of a circle. 180 degrees is a half of a circle. Here we've taken the 90-degree angle and we've cut it in half and we get a 45-degree angle, for example. And we can look at angles of any size. Remember, what this really means is those 1-degree pie slices, there would be 45 of them in this angle on the left. Okay, so why are we talking about that today? Well, we want to compare things that are the same shape. And in particular, we're going to start with triangles. So here we have 2 triangles, and they are not the same size. But we do say that they are the same shape because they have the same size angles on their interior. And in this case, we call the triangles similar. So again, similar means that they have the same shape. And by that, I mean that they have the same size angles. And the way we indicate which angles are the same is using these little symbols you see here. For example, angle B has the same number of marks, 2, as angle Q. So off to the right here, I'm going to write angle B is equal to angle Q. Okay, and we can also look at angle A and ask ourselves which angle is that equal to? It has only 1 mark, so it's the same as angle P. That means they have the same measure. By the way, this little thing that looks like an L shape, that's a symbol for an angle. So angle A equals angle P, angle B equals angle Q, and also we have our third angle, angle C, which has 3 marks on it, we're being told is the same as angle R. All right, now a new symbol that we're going to work with is this little tilde symbol, a little squiggle, and this means that one triangle is similar to another. Now, the way we name triangles is using the three letters that are at their vertices. The vertices are the little points. Okay, so for example, the triangle on the left could be called triangle ABC, but it could also be called triangle BCA or ACB, any order, it doesn't matter. We usually go in alphabetical order if we can, but you don't have to. However, once you decide what you're going to call the triangle, like I called this one ABC, if you want to say it's similar to another triangle, you have to be careful with the order of the letters that you use. For example, this triangle could be called QRP, but it would be wrong to say that triangle ABC is similar to triangle QRP because that implies that the first letter, which represents angle A, has the same angle measure as the angle that comes first in the other one, which is angle Q. And A and Q are not the same. So if you're going to say two triangles are similar, once you've decided how you're going to name the first triangle, you have to be very careful about the second. Since angle A is equal to angle P has to go first when we name the second triangle. Since angle B is equal to angle Q has to come second, just like B did. And since angle C is equal to angle R has to come third like angle C did. So if you see this indication that two triangles are similar to each other, it's really packing in a lot of information because it's not just telling you the two triangles have the same shape, it's also telling you specifically which angles are equal. Okay, so one of the things that's going to be helpful to us, one fact that will be helpful for us to know, is that if you add up all of the inside angles, there are three angles in each triangle, if you add those up, you'll always get 180 degrees. The reason that this is helpful is if you only know two angles in a triangle, you can always figure out what the third angle is. So let's look at an example. Here I have two triangles, triangle ABC and triangle QRP. Let's start with triangle ABC. We know that triangle ABC has angle A equal to 27 degrees and angle B equal to 45 degrees because they're marked. But notice that angle C is not marked. We're not sure what the measure of that angle is. But we do know that if we add all of these up, they have to sum to 180 degrees. So I'd like you to pause and think for a moment, how could I find the measure of angle C knowing that information? So wouldn't it be true that to find the measure of angle C, we would take 180 degrees and subtract the two angles that we already know? All right, so let's use our calculators and subtract. We're going to take 180 degrees, oops, I hit the wrong button, and subtract 27 and also subtract 45, and let's see what's left. So that would mean that the remaining angle would have to be 108 degrees. All right, now before we talk about the missing angle in the other triangle, I would like to make an observation. Notice that these two triangles appear to have two at least of the same angles. Angle B is the same as angle Q, and angle A is the same as angle P in measure. All right, so wouldn't it make sense without even finding the measure of angle R? Wouldn't it make sense that angle R also has to be the same measure as angle C? Because we know that to find the measure of angle R, we would have to do the same process, subtract 180 minus 45 minus 27. So that's an important concept. This is referred to as um, the angle-angle condition for similar triangles. That is to say that if we know two angles are the same, then we know all three angles are the same and the two triangles must actually be similar triangles. So we actually can know two triangles are similar by knowing two angles are the same. We don't even need to know the third angle. But we do know the third angle in this case because we already subtracted. I'm going to mark it as 108. Okay, now I would like you to take a piece of paper and a pen, pencil, and I'd like you to test yourself. Pause this video and see if you can fill in names of the triangles which are similar to each other. I'm going to start by naming the first triangle ABC. I would like to know if you can figure out what the order of the letters should be for the other triangle. Okay, so uh, paying attention to which angles are equal, A is equal to angle P, B is equal to the measure of angle Q, and C has the same angle measure as R. So you should have written triangle PQR. Okay, now let's talk about the types of contexts of problems that we're going to be looking at that's motivating us to talk about similar triangles. So similar triangles are used in many situations to measure lengths indirectly. The applications in which we use similar triangles often involve certain common diagrams. And I have found that being able to draw these diagrams is very important in understanding how to work these problems. And actually, there are not a lot of different diagrams that you come across. They're all pretty similar to these four diagrams. So, or usually they are. So, one of the contexts that we will talk about is when the sun is shining and casts a shadow on the ground. So, you need to be able to draw a picture of that, and you need to understand where a triangle comes into play. So, here on the left, let's call this diagram A. You can see our little sunshine here, and the sun is casting or shining down on this tree, which is casting a shadow on the ground. So what happens is the tree acts as one side of the triangle. The shadow on the ground acts as another side of the triangle. And if you can imagine, the sun is shining, right? It's shining brightly past the tree, but the tree is blocking the light below this line. So that line, you can think of it as the line of sight from the top of the tree down to the tip of the shadow is the third side of the triangle. And in a diagram like this one, you would Also, think of the tree, the straight up and down side of the triangle as forming a 90-degree angle to the ground. We talked about 90-degree angles. So this would actually be a right triangle. Now, you can see that in this particular diagram, we have some measurements marked off. That information would be given to you in the problem, but you would need to be able to draw the picture and then go ahead and label any values that they tell you. Let's talk about another context in which we will see triangles in this class. Sometimes we have problems that talk about a ladder leaning against a wall. Okay, so first of all, you have some wall from some building. You can assume that this wall is built straight up and down, forming a right angle to the ground. So when you're drawing a picture and a diagram and you're putting in the wall, you can draw it as a straight up and down line with a little right angle. The ground is also a side of the triangle that is going to appear in this diagram. So you've got the side of the building as one side of the triangle, the ground is another. There's a right angle between them. And then when we lean that ladder against the wall, that's where we get the third side of the triangle. And then in the problem, they will give you information, things like the measures of angles or the length of the ladder, and you need to mark those on your diagram as well. Another type of diagram that you will see commonly, this is going to be in some of the more challenging problems because it actually involves two triangles, but it's one nested inside of the other. This would be a situation like a person walking away from a lamppost, creating a shadow on the ground. Okay, so the lamppost, much like a tree or a building, we can think of this as a vertical line segment, and it is going to form a right angle with the ground. You can think of the person as being straight up and down as well. So you can draw a line here, and that person is forming a right angle to the ground as well. The ground, of course, is important. This is going to be a side of a triangle. It's actually going to be two triangles. We'll see in a moment. And then the light that is shining down, just like the sun did a minute ago, the light projects all up here, but the person is blocking the light. So from the line of sight of the person's head down to the ground at the tip of the shadow is here, we're going to have the third side of our triangle. But there are actually two triangles here. There is the triangle formed by the lamppost, the ground, and the line of sight from the lamppost past the person's head to the tip of the shadow. And then there's a smaller triangle formed by the person, the shadow on the ground, and the line of sight from the person's head down to the tip of the shadow. So there's a larger blue triangle and then the smaller red triangle within it. Here's a similar diagram that we would need to be able to draw in diagram D here. It's again an object casting a shadow, except we're talking about two different objects. So the shadow of two objects at the same time of day, and the tips of their shadows both meet at the same point. So here's the sun up here shining down, and the tree is one of our two objects forming a right angle with the ground. Here's the ground out to the tip of the tree's shadow, and we have the line of sight from the top of the tree down to the ground, just like we saw before in diagram A. But incorporated into that is this flagpole. The flagpole is again forming a right angle with the ground. Here's the shadow of the flagpole on the ground in front of it. And from the line of sight from the top of the flagpole down to the tip of its shadow forms a smaller triangle within the larger blue triangle. So I wanted to go over these diagrams with you before we actually try to do any calculations. I want to practice with you drawing diagrams like these. So let's look at exercise number 1 here. And we're not going to try to solve for any kinds of lengths or measurements or anything. We're just going to try to represent the scenario in a diagram and identify any triangles that are formed. If you would like to pause the video and try to draw the diagram on your own, that would be great because that will give you time to think about the problem. And then once you think you have the solution, you can compare it to what I do next. And that will help you to see if you're on the right track or how you need to adjust your diagram. Okay, so number 1 says a 6-foot ladder leans against the side of a house, forming a 30-degree angle with the ground. A 12-foot ladder leans against the side of the same house at the same angle. Okay, so we have a 6-foot ladder leaning against a house. We have a 12-foot ladder leaning against the house. Let's go ahead and just try to draw that. Well, they do observe that the first ladder is forming an angle of 30 degrees with the ground. Also remember that anytime you have a ladder leaning against a house, like in diagram B here, you can think of the house as forming a right angle with the ground as well. Okay, so we're going to take that idea. Now, when I work these in class, I have students do a variety of things, and they're not wrong. Some students think of uh, drawing one ladder leaning against the house on one day, and then here's the house on another day with a different ladder leaning against it. So they draw 2 separate diagrams. Other students combine them into one. I'm going to go ahead and go with the drawing 2 separate diagrams because sometimes when we draw them in the same diagram, the triangles overlap and it's a little more challenging. So I'm going to I'm going to pretend like it's on 2 separate days. So here's my house. Now, do you actually need to draw a house? No. You can just draw a line really, just like, boop. But I made it a little rectangle just to kind of give the impression of a house. All right, and then we know the house is sitting on the ground and hopefully it's not a leaning tower, so it's gonna form a right angle with the ground. On this ground is also a ladder. The ladder is situated to lean against the house. So my ladder leaning against the house. Okay. All right. Notice that I marked the right angle and I'm also going to mark the 30-degree angle. They said that it's leaning at a 30-degree angle against the house. I'm sorry, with the ground, excuse me. So that would be this angle right here. So that's 30 degrees. You should mark any measurements that they give you on your diagrams. All right, so I'm going to highlight in red the triangle that has been formed. We have the ladder forming one side of the triangle, the portion of the ground between the ladder and the base of the house, and then we have the house itself. So there's one triangle in this diagram. Now I'm going to worry about the 12-foot ladder. So it's going to be a very similar diagram, except it's a longer ladder. We're still going to have the house. We're still going to have the right angle with the ground. Okay, and now when we're going to draw our ladder, remember they said that it's at leaning against the house at the same angle, 30 degrees, but it's a longer ladder. So if it's going to lean at the same angle, and you don't have to get the drawing exactly correct. I'm just explaining to you why I'm drawing it the way I'm drawing. I'm going to draw it as a longer ladder. It's going at the same angle, so I'm going to mark 30 degrees. And just, just because I'm trying to be as exact as I can, I'm making it, hit the ground at about the same angle that I did over here. But you don't have to have that perfect, as long as you have the other triangle. Now, one thing I have not done yet is to mark the lengths of the ladders. So I'm going to mark a 6 foot on the other part of the diagram and 12 foot on this one. So usually when we put a number in the middle of a line segment, this indicates the length of that line segment. That's important to understand when you're reading a diagram. Anytime that they put the number right in the middle of a line like that, they're talking about the length of that line. For example, and they did not tell us the height of this building, let's pretend we were looking for the height of the building and I wanted to call it X. I would put it right in the middle of the height of the house. Okay, but anyway, this is the diagram if you draw it like the ladders are there on 2 separate days. Just for kicks, I'm going to go off to the side and show you. Sometimes my students prefer to have the 6 foot ladder here and the 12 foot ladder here. So they draw the diagram one inside of the other. That's just a little trickier sometimes to visualize. That's why I went with this version instead, but the other is not wrong. You would, oh yeah, I didn't put my 30 degrees and my 30 degrees here. So that's another alternative. Okay, let's look at another scenario. Again, it'd be a good idea to pause the video and try to draw this on your own. So it says a house is 19 feet tall. Its shadow is 30 feet long at the same time that the shadow of a nearby building is 285 feet long. Hint, since it is the same time of day, the sun hits the roof of the house at the same angle it hits the roof of the nearby building. Okay, so we're going to draw a house and I'm going to draw the building as being a little bigger. Can you guess why? Think about why did I decide that the house must be a little bit smaller than the nearby building in height? Well, it's because the shadow of the house is 30 feet long and the shadow of the building at the same time of day is 285 feet long. So it must be that the building's a little bit bigger. Again, you don't have to have it perfectly proportionate, but that's good to understand. All right, now let's talk about the shadow. So at the same time of day, the sun is going to shine down at the same angle on each of these buildings. So but I'm going to draw the sun uh, in two different positions just to make a point. So if the sun is shining down on this building, remember from the line of sight from the top of the building down to the ground, we see the shadow here and it forms a triangle. The building is at a right angle to the ground. They tell us that the shadow is 30 feet long. I'm going to highlight, if I can, the shadow in green here. This is my shadow. You don't need to highlight it. You just draw the little line. That's fine. But this is my shadow. Okay, so my shadow is 30 feet long. Now I want to put the 30 in the middle of that line segment, so 30 feet. So we know that it's that piece in green that I'm referring to. The house is 19 feet tall. So for example, I could put a 19 right here in the middle of the height of the house, in the middle of the segment that is like the wall of the house. Okay, and that's the triangle that's formed. Now, if it's the same time of day, the sun is going to form the same angle with the building. I drew it a little weird. That's okay. Maybe the sun would be more over this way. Okay, really the sun is millions of miles away, but the angle is the important thing. So here we go. So we have a right angle with the building. They tell us that the shadow, which is this part right here, the shadow is going to turn out to be 285. So right in the middle of that green part, we put 285 feet. Okay, they didn't tell us the height of the building. In fact, probably in a problem like this, we would be looking for the height of the building. But remember, this problem is all just about getting used to drawing the diagram. And we're supposed to identify where we see the triangles here. So the triangles are here and here. Another observation that's important when we're talking about two different objects at the same time of the day is made right here. The sun hits the roof of the house the same angle it hits the nearby building. How can we indicate that in our diagram? Well, the sun hitting the house forms this angle here. Okay, this is the angle formed by the sun hitting the roof of the house. It's going to be the same size angle over here. So you might want to put a mark to indicate that these angles are the same size. Now, one of the things that I've noticed that students get kind of hung up on is the idea that a shadow looks like the object that formed the shadow. For example, if you look up here in diagram A on the left, you can see they even indicated that in this diagram. You can see the shadow kind of looks like a tree, the shape of a tree. That is not important. When you draw your shadow, you can mark it as shadow, but just draw it as a straight line. Same thing down here. I highlighted it in green simply to show you where it was, but we don't need that. That's not because I'm trying to make it look like the building. Trying to erase it right now. It's not letting me. There we go. Here, this is my shadow. You just draw a line. You don't have to draw anything that's the shape of the building. Okay, the point of these diagrams is not to be artistic. It's great if you can be, but the point is to be able to identify what triangles we're going to be working with and to label whatever dimensions are gonna help us in the problem. Okay, now speaking of comparing two triangles. So when two triangles are any objects really that are the same shape, when they're the same shape but not the same size, they're going to have dimensions that are proportional. What does that mean? That means that the dimensions of one can be found by multiplying each of the dimensions of the other object by the same value. All right, so before I go on to, by the way, this value is called a scale factor, but before I talk about the definition in detail, here's an example of two triangles that are similar. Remember, similar means they're the same shape, so they have the same angles. So here we have 30 degrees. Here we have 120 degrees. And then we also have another 30-degree angle over here. Okay, so these are definitely similar triangles. And I want you to take a moment and think about what's a number that you could multiply 3, 3, and 6 by, and it would result in the values 12, 12, and 24. Again, what number would you have to multiply each of the numbers in the small triangle by to get the values that are the lengths of the sides of the larger triangle? So you probably said 4, right? 3 if you multiply it by 4 is 12. Again, 3 if you multiply it by 4 is 12. And 6 if you multiply it by 4 is 24. When two triangles are similar, there will always be this magic number like the number 4. In this case, 4 is called the scale factor. Okay, now how can we get that value? Well, you probably asked yourself, what do I multiply 3 by to get 12? But that's the same thing as dividing 12 by 3. Division can be written as a division symbol or one number over the other. 12 over 3 is 4. But it has to be corresponding sides. So what do we mean by corresponding sides? Corresponding sides are between corresponding angles. You see how the 3 is between the 30 degrees and the 120, the red and the yellow? And the 12 is also between the red and the yellow. So these two sides correspond to each other. So if we want to find the scale factor, we can divide 12 by 3. But we also could have used the 6 and the 24. See how the 6 is between the red and the purple angles of 30 degrees? And this guy's between the red and the purple angles of 30 degrees. So these two sides correspond to each other. So to find the scale factor, I could also have divided 24 by 6 and got 4. It doesn't matter as long as you divide the larger triangle by the smaller triangle, and as long as you're sticking to corresponding sides. Now, just for practice, let's go ahead and name these triangles. So if I call the first triangle ABC, what would I have to call the second triangle so that the angles are correctly corresponding? So it looks like A is equal to D, B is equal to E, and C is equal to F. By the way, it wouldn't be wrong to relate, since there are two 30-degree angles, we could switch them and it would still be correct. But I like to go with the other one because visually it makes more sense. It's easier to follow. All right, so now let's talk about how we name sides. So you name the side of a triangle based on the letters of the vertices at each end. So for example, the side of length 6 on triangle ABC is called AC. And the side of length 24 that corresponds to it on the other triangle is called DF or FD. The order doesn't matter, though we usually go in alphabetical order. All right, so what this little equation over here is meant to say is that the side DF, which is a length of 24, if we divide it by the length of the side AC, which is 6, we get our scale factor of 4. but we could also use the other corresponding pairs of sides. So let's see, this version says to look at DE and AB. So DE would be here and AB would be here. So this is telling us divide 12 by 3, which is also 4. Or in the middle here, we have EF over BC. So that's telling us the side EF, which corresponds to the side BC. If we divide 12 by 3, we also get 4. So this is showing all the ways that we could divide corresponding side lengths to get the scale factor, which is 4. Now, really, you can divide the smaller triangle by the larger, but that gives you a fraction, and you have to work things differently. So for consistency, in this class, we're always going to find the version of the scale factor that results from dividing the side of the larger triangle by the corresponding side of the smaller. All right. So let's go ahead and find the scale factor for triangles that are uh, in an application context in a word problem. So let's look at number 3. The instructions at the top say each diagram represents a pair of similar triangles in a real life scenario. Find the scale factor. So diagram 3, so we're looking at the left side of the screen over here. We're going to focus on item 3 first. So you can see two triangles drawn, one next to a man and one next to a tree. What's going on here? It says the sun casts a shadow on two objects at the same time of day. The person's shadow is 8 feet long. The tree's shadow is 22 feet long. Okay, so apparently the sun is over here shining. If it's at the same time of day, remember that tells us about the angle formed. The angle formed from the top of the tree down is going to be the same as the angle formed from the top of the man's head down to the ground. Another thing that we know is that we can always put a right angle for the person standing and a right angle for the tree. So how is it significant to us? Well, they mention a pair of similar triangles in each problem. We just identify that these are similar triangles. In fact, since we know that they have two angles in common, remember how we mentioned that angle-angle idea. So this angle down here must also be the same in order for them all to add up to 180 degrees. Remember that? Anyway, what we're supposed to be doing here is using the scale factor idea, but that only works because these are similar. That has to be the case. If they were different shapes, scale factor does not work. Okay, so how do we find the scale factor? We take the longer, or let's say a side of the larger triangle, and divide it by the corresponding side of the smaller triangle. Well, we only know two measurements, and luckily 8 feet and 22 feet. These are corresponding sides. So think, what would I divide by what? I would divide 22 by 8 to get the scale factor. So what's 22 divided by 8? That's going to be 2.75. 2.75 is the scale factor. Each dimension of the larger triangle is 2.75 times bigger than the lengths of the sides of the smaller triangle. Okay, let's try another one. Number 4, we have a child standing 320 inches from a light post, has a shadow that is 80 inches long. And you can see that this is one of those problems where we have two objects forming two triangles, one inside of the other. We saw another one of these up here on the uh, diagram C and D. Okay, so I'm going to give you a little tip here. Whenever you have two triangles, one inside of the other, draw them out separately. This will help you to avoid making mistakes. Okay, so one of the triangles, the big triangle, is triangle ABD. So I'm going to draw that one first. Okay, so we have A, B, D. I'm also going to put any dimensions I know on here, but this is one of the reasons why I have you draw it separately, is because length BD is something that you really need to be careful with. Okay, looking at this here, a lot of times people don't understand what the implication is. Do you see how there's the number 320, there's the letter C, and then there's the number 80? What do you think they're indicating here? They're indicating that the length BC is 320, and the length from C to D is 80. But we're looking for an entirely different length. We're looking for everything from B to D. So can I just write 320 here? Because that's what I often see students do, is to write 320 here. No, why not? Because to get from B to D, you have to go from B to C and then to D. So you have to add 320 plus 80. This is going to be actually 400. 400 inches is the distance here. Okay. I also can mark the right angle. And now I am going to draw the smaller triangle, okay, with the ECD. Okay, smaller triangle, ECD. Now, we do know C to D is 80, right? So we can mark that. We also can always, when we have a person standing on the ground, we can think of that as forming a right angle. Okay, and then, but in order to know these are similar triangles, we actually need to know that two of the angles are the same. But notice that angle D is the same in both diagrams. This is angle D, this is angle D, that's the same angle. So we know that two angles are the same, so these are definitely similar. Triangle ABD is similar to triangle ECD. So that means we can find the scale factor. How do we do it? We divide the side of the larger by the side of the smaller it corresponds to. And so what would we divide by what in this case? Okay, if you said divide the side of length 400 by the side of length 80, you're correct. The scale factor is 5. The lengths of the dimensions of the larger triangle are 5 times bigger than those of the smaller triangle. Okay. Now, this is all building up to indirect measurement, being able to determine a length, a distance that we'd like to know using the comparison of two objects that are the same shape. So this is finding a missing side using a scale factor. To find a missing side of a larger triangle, you take the scale factor and you multiply it by the corresponding side of the smaller triangle. That makes sense, right? Because the triangle is larger, you have to multiply the smaller triangle by the scale factor to get a bigger number. On the other hand, if you're trying to find the side of a smaller triangle and you know the side of the larger triangle, you need to make it smaller by dividing by the scale factor. So there's two scenarios. The first one is where you're trying to find the side of the larger. So you know the smaller one, you need to make it bigger by multiplying. The second is you're looking for the side of the smaller, so you need to take the known larger side and divide it to make it smaller. So we're going to practice this with these exercises here. So let's look at number 5. By the way, in each of these cases, we have a pair of similar triangles, or otherwise this wouldn't work, right? This idea of scale factor only works when we have the same shape. Okay, so let's look at number 5. I'm going to highlight the corresponding sides. So we can see that the side of length 15 is between the two marked angles, and so is the side B. We can see that the side of length 12 here corresponds to the side of length 6 here. It's between the angle that's not marked and one of the marked angles. And similarly here, this side of length 12 corresponds to side A. Okay, so out of these pairs of corresponding sides, the only one where we know both are the red, the ones I just marked in red, the 12 and the 6. So what do we do to find the scale factor, which I'm going to indicate SF for scale factor. The scale factor, we're going to take the larger of the two corresponding sides, 12. We're going to divide it by the smaller, so that would be 2. In other words, the bigger triangle is twice as big as the smaller triangle. Okay, now we're going to use that to find A. So looking for the length of side A, are we looking for the side of a larger triangle or the side of a smaller triangle? We're looking for the missing side of the smaller triangle. So we need to take our 12, the corresponding side from the bigger triangle, and make it smaller by dividing it by the scale factor. 12 divided by 2 should give us A, which means A should be 6. And then we're going to do the same thing to find side B. So again, we're looking for the smaller side. I'm sorry, we're looking for a side from the smaller triangle by comparing it to the larger one. So we need to take the number 15 on the corresponding long side of the larger triangle. We're going to divide it by the scale factor to make it smaller to get side B. So B is going to be 15 divided by 2 is 7.5. So those are our two answers. A is 6 and B is 7.5. But we had to calculate the scale factor to get those answers. All right, let's move on to number 6. So on number 6, there's actually something missing from the diagram that was supposed to be there, which is the mark that indicates this bottom right corner angle is the same as the one on the other diagram. That way we know that the two triangles are similar. That was supposed to be there, but I accidentally left it out. Okay, so let's highlight in different colors the corresponding sides. All right, so which side would correspond to the side of length 15? Notice that that side is directly across from the right angle. We would call that the hypotenuse, by the way. So it has to correspond to the hypotenuse in the other triangle. Okay, and what would the side that touches that one and meets also touches the right angle, which is labeled A, what would that correspond to? So in the other triangle, the one that touches the orange and also touches the right angle is going to be the side of length 8. And then that just leaves the third side, B, must correspond to the side of length 6. Okay, now out of the orange, the dark blue, and the light kind of bluish teal, which of those colors do we know the lengths on both triangles? That would be the 15 and the 10. So to get our scale factor, we're going to divide the 15 in the larger triangle. We're going to divide it by the 10, the corresponding side of the smaller triangle. So our scale factor will be 1.5. All right, now let's look to see what we need to find. Do we need to find the sides of a smaller triangle or a larger one? We're looking for A and B. Those are both in the larger triangle. Let's scroll up a little bit. Remember, if you're looking for the side of a larger triangle, ooh, that's a mess. What do? You take the scale factor and multiply it times the side of the smaller triangle. You have to get bigger to see what the larger triangle side is. So we're going to take, if we're going to find A, for example, we have to take our scale factor, 1.5, and multiply it by 8, the length of the side of the corresponding side in the smaller triangle. 1.5 times 8 is 12, so A is 12. Okay, now let's talk about finding B. So for side B, it corresponds to the 6. So we are going to have to multiply 1.5 times the length 6. That's going to give us 9. You see how we got bigger numbers? That's good because this is a bigger triangle. Multiply to get bigger numbers from smaller numbers. Okay, and then let's look at number 7. So for number 7, we have one triangle inside of the other. And what did I say that we need to do to prevent confusion? Draw 2 separate triangles. So I'm actually going to label all of these vertices of my larger triangle and also the vertices of my smaller triangle, just so that we can talk about it. So let's call the smaller triangle A, B, C. And we'll have our larger triangle, it's still going to be A, but we'll call this D and E. Okay. All right. So we have triangle, the big triangle is going to be ADE. And the smaller triangle is going to be ABC. But let's draw them separately so it's not so confusing. So here's the smaller red triangle. I'm going to put my right angle in there and label my A, B, and C. And then I'm going to draw my larger triangle right next to it. Now we're going to have A, D, E. E is also a right angle. And notice that we do have an angle in common here, A. This is the same angle A in both triangles. And that's good because that's how we know we have similar triangles. We have a right angle in common and then we have angle A in common as well. So they're definitely similar, so we can find a scale factor, but let's go ahead and label the dimensions that we know and the dimensions that we're looking for. In the red smaller triangle, we have a height, the length of the side BC is 75, and the length of the side AC is 150. In the larger blue triangle, the length of the side DE is unknown. They've marked it with an X, so we want to mark that as well. And then what about this? Do you remember how to deal with the length of the side AE? So if you said we need to add 150 and 180, you're right. What is 150 plus 180? That's a total of 330. So the side AE has a length of 330. Okay, so are we looking for a missing side in the smaller or the larger triangle? We're looking for a larger side, X, the side DE. Remember, if you're looking for a larger, you have to multiply the scale factor times the side of the smaller triangle it corresponds to. Multiply, not divide, because we need to make this 75 that it corresponds to. We have to multiply it by something to make it bigger. The scale factor is what we're going to multiply by. So first, let's find the scale factor. We're going to take our two corresponding known sides and divide the larger by the smaller. So 330 divided by 150. 330 divided by 150 is 2.2. So the blue triangle is 2.2 times as big as the red triangle. So if we want to find x, we have to take the scale factor 2.2 and multiply it by the corresponding side of length 75. So 2.2 times 75 is 165. Okay, now let's look at a couple of application problems where we have to do everything that we've just mentioned. We have to draw diagrams, identify the triangles, find the scale factors, and use the scale factors to find the missing sides. So number 8 says a 6-foot ladder leans against the side of a house, forming a 30-degree angle with the ground. Sound familiar? And a 12-foot ladder leans against the side of the house at the same angle. So that's the same diagram we drew before. And we're going to use it here. So we're going to have, let me do this. We're going to have a house. Again, you don't have to actually draw the whole house, but something to indicate a house with a 6-foot ladder leaning up against it at a 30-degree angle. Here's our 90-degree angle where the building meets the ground. And this is our 6-foot ladder. And then the same house, we have a 12-foot ladder leaning up against it at the same angle. And it also meets the ground at a right angle. We know that the base of, so the new information is that the base of the 6-foot ladder is 3 feet from the house. So we're going to put 3 feet on our diagram to show this is the base of the ladder. And this is, by the way, the base of the house. And they're telling us that they're 3 feet apart. Okay. And then it asks, how far is the base of the 12-foot ladder from the base of the house? So they're asking us to find what I'm going to mark X right here, the distance from the base of the ladder to the base of the house. Well, actually here. Okay. All right, so to figure that out, we're going to use the fact that these are in fact similar triangles. Why are they similar? Because they both have angles of 30 and 90, which means their third angle must be the same as well. All right, now scale factor. How do we find the scale factor? Well, we look for a pair of corresponding sides that we know both. We know the lengths of the ladders. So we take the length of the longer ladder from the big triangle, divide it by the length of the smaller ladder. 12 divided by 6 is 2, telling us that the larger triangle has dimensions twice as big as the smaller. And then what do we do next? We're going to find side x. Remember, we're finding the side of the larger. We're going to multiply the scale factor times the length of the smaller. The corresponding length to the side x would be 3 feet. So 2 times 3, so that's going to give us 6. So that tells us that the second ladder, the 12-foot ladder, had to be 6 feet away from the house. Okay, now let's look at number 9. A house is 19 feet tall. Its shadow is 30 feet long. At the same time, the shadow of a nearby building is 285 feet long. Do you remember that drawing that we did? So I'm going to draw the house a little shorter than the other building because it has a smaller shadow. The same time of day the sun is shining down, it's going to form the same angles for both buildings. Shadow is going to be down here, right? In both cases. Both cases we have a right angle where the building meets the ground, and because they form their angles are formed by the sun, this top angle from the building down will be the same on both diagrams. Now let's go ahead and put in some dimension. Well, let me highlight the triangles that we just formed there. So we have a smaller triangle and we have a larger triangle, and they're similar to each other. They're proportionate, so they have a scale factor. Let's put in the dimensions now. We know that the house is 19 feet tall, and we know that the shadow that is formed on the smaller on the house is 30 feet long. In the case of the other diagram, we know the shadow is 285 feet long, and they're asking us how big is the building. So I'm going to mark the height as X. By the way, it doesn't matter if you put the X out here or you put it right next to this side of the triangle. Same thing with the 19. Either way, because the house is going to be the same height on both sides, right? Okay, so how do we find the scale factor? We have to look for corresponding sides. We know that highlighter does not want to work. All right, so we know that the 30 corresponds to 285. So we divide always the larger by the smaller, 285 divided by 30 to get our scale factor. Let's see what we get. 285 divided by 30 is 9.5. So that's our scale factor. The larger triangle, in other words, is 9.5 times bigger in dimensions. Okay, so now we're going to look for x. Is x part of the bigger triangle or the smaller? It's part of the bigger. So to get the bigger from the smaller, we have to multiply by the scale factor. So x is going to be 9.5 times. Now let's see, what's corresponding to the height of the building? The height of the house. So it's going to be 9.5 times 19. By the way, that's not supposed to be an x. That's supposed to be a times. I'm going to use a dot to represent the multiplication so it's not so confusing. 9.5 times 19. Let's see what that turns out to be. 180.5. So x equals 180.5. And the units, by the way, in this case are feet. We should include the units. Okay, I hope you found this video helpful. If you did, please give it a thumbs up. That'll help other students to find the video.